So, good afternoon, students. Now, in today's class, we have seen a particular article based on the boundary layer theory, and the topic is the boundary layer flow along a flat plate. That is, we are considering a thin flat plate, and we have taken that the steady. You remember, time independent. The flow is not depending on the time. Steady flow of an incompressible, that is the density is constant, okay, viscous fluid past a thin flat plate, and the plate flow is with an uniform velocity. Now you remember this part, that is the uniform free stream velocity that is constant. In the boundary layer main derivation problem, the mainstream velocity or free stream velocity was functions of flow direction and the time t. But in this article, we have taken that the free stream velocity is a constant one. The leading edge of the thin plate, that is the starting point, or the starting point of the thin plate, is considered as origin. Yeah. And the x-axis is considered along the direction of uniform stream, or we can say that the x-axis is taken along the length of the surface and y-axis is taken perpendicular to the. So this is our usual boundary conditions. Now, as just little while ago I have stated that that we have taken the steady flow, so del u del t, and this term will cancel. Similarly, as you have taken that the capital U, that is the free stream velocity, this is constant, so this is also. So this is our remaining boundary condition, boundary layer equations with the boundary condition, that is at y equal to 0 means at the surface both the velocities are 0 as the surface is at rest, and if we go away from the surface, okay, that is that free stream case, the velocity is capital U. Now if you look at you have to solve the equation 1. Now if you look at the equation 1, there are two dependent variables u and v. So we consider this we introduce this particular function psi by using this assumption. This is a type of this types of function is called stream function, which we will study in our unit 2. Okay, so this is the definition: u equal to del psi del y and v equal to minus del. Now one question arises: can we take these types of function? Yes, it is possible. You can take any function provided it must satisfies your continuity equation, means this one. Okay, so if you replace the value of u as del psi del y here and v as minus del del x here, you will see that your continuity equation automatically satisfies. Okay, so this is the advantage. Now we try to find what might be the order of delta, or what might be the expression of delta, or what is the formula of delta, or in delta what type of expression might appear. Let us see. So in the derivation of boundary layer, if you remember, you have obtained this types of equation. You can recall your previous notes. Means delta square is nothing but, this is similar to your viscosity nu. So delta will be root over of nu. Now if you go to your Reynolds number definition, Reynolds number is characteristic velocity, characteristic length divided by the nu. So means Reynolds number is inversely proportional to nu. So what we get, our delta, it will be inversely proportional to 1 by Reynolds number. Okay, because your delta is similar to root over nu, and root over nu is proportional to reciprocal of the Reynolds number. But now you see delta, this is thickness. Okay, so this constant of proportionality must be in terms of some length L. Otherwise, this relation will not vary. Relation will not valid. Why? Because your delta, its unit is length. Look at your right hand side. 1, it has no unit. Reynolds number. If you go back to the definition of Reynolds number, this is the ratio of two forces, inertia force by viscous force. Okay. So Reynolds number is also unitless. So how this is possible? So for the constant of proportionality must be equal to the length L. Okay, and now we substitute the expression of the Reynolds number. Okay. So this will be the form of your delta. Now, what is length L here? This is the length of the surface, and in this particular problem, our capital L coincides with X. So, we can replace for this problem L by X, because the length, this is the length and this is nothing but your X. Now, we are using one transformation. So, for that transformation, we define a new variable eta as y by delta. Now, remember, it is not necessary that you can or it is the only transformation, that is eta equal to y by delta. We have to transform, or we have to choose our transformation. You remember this point, huh? We have to choose our transformation in such a way that the partial differential equation, means this one, it becomes an ordinary one. So for that, we define a new variable eta as y by delta. Now we replace the value of delta, okay, and this is another transformation, that is small u by capital U is equal to function of eta. Now d psi, that is the total stream function, just in previous page, this can be written in this form. Okay. Now what is your del psi del x? Just you go back to your previous page. Del psi del x is your v. And what is the order of v? This is nothing but delta. You recall the notes for your boundary layer equation. So this delta is very small compared to your u. So that's why this part is cancelled, because its value is there, but its value is very small compared to this one, just from your boundary layer one. And this is very much less than u. For understanding, this is for understanding. So this d psi, del psi del y is your u. Now we substitute the value of u from there. What is small u? Capital U into f of eta. Okay. Now what is your dy? So what is our eta? Eta is equal to y into root over u by nu x. Just we recall it. What is our eta? Y into u by nu x. So this will be, what is your y? Eta root over nu x divided by. So what is our dy? It will be d eta root over nu x by u. Because we are studying at this particular region, not at separate values of it. For a particular line, we are studying the equation across the boundary layer. So if we study across the boundary layer, so for a particular segment, the values of x are same. So now if we integrate it, we have obtained this part, and we denote this part as f of eta. Okay. So now our u, this is del psi del y. Okay. So for that, you derive, you differentiate your psi with respect to y by the chain rule. First you differentiate your psi with respect to eta, then eta with respect to y. So you are getting this expression. Similarly v, this is minus del psi del x. So if you simply go with simple mathematics, you will obtain your v as this one. Del psi del y. After knowing your u, you can easily find your del psi del y. Then del psi del x and del 2 psi. So now what we do, we replace this u, v, del psi del y, del u del x, del 2u del y square in the equation 1. We replace these terms. After replacing, this is the equation what we obtain. And after some simplification, this is the new equation. So what is the advantage? You see, in the first equation, this is an partial differential equation. So after using this transformation, this is the transformation, what I have said, eta as y by delta, and this is. After using this transformation, the equation 1 becomes an ordinary differential equation, and this equation is known as the Blasius equation. And those corresponding boundary condition, this is the corresponding boundary condition for the variable y, u and v. Now your new variables are f is the dependent variable and eta is the independent. So those boundary conditions are expressed in terms of the new variable. So this is one boundary condition, this is another boundary. So I request you to please go through this note and compare this with your video, and if you still have any question, then you can ask. Yes. So now we come to the next article, that is the momentum integral equation. So this is our original boundary equations, okay, corresponding boundary. Now if the system is steady, then we will cancel this term, okay. So now you look at this part. You have taken your capital U is a function of x comma t. Now if the system is time independent, that is steady, so then capital U will be a function of x only. So if your capital U is a function of x only, this partial derivative, it becomes an ordinary one. Okay. So we are there. Now we integrate this equation with respect to y across the boundary layer. Means this is your boundary layer. You are integrating this equation 2 along this line. So you see the line starts from this point. So here your y is 0. So that's why lower limits are 0. Your line ends at this point. Okay, it is not going beyond the boundary layer. Because why? Because you are dealing what is the problem inside the layer. So that's why the upper limit is delta. So this is our equation number 3. So from this equation we select this term. So we have written. So by parts, first term into integration of second. Now its integration is u because it is in differentiation form. Then differentiation of first minus into integration of second. Okay. Now we substitute the limit values. Okay. When the lower limit is substituted, when y is 0, what is the value of u? When y is 0, both the values of u and v are 0. So when the lower limit is substituted, this terms gives 0. But when the upper limit is substituted, means when your y is delta, the value of small u is capital U. Okay, so small u is capital U. But we don't know what is the value of v at delta. Now we replace del v del y from our continuity equation. So from this continuity equation, your del v del y is minus del u del x. So we have substituted it. Okay, this term is obtained. Now look at this in part. If you integrate del v del y with respect to y, means if you integrate your derivative, you are getting v. Okay. Now substitute the limit values. 0 to delta. What is the value of v at 0? V at 0 is 0. So the value of v at delta is nothing but integration 0 to delta del v del y dy. Please, you check it. So we are substituting the value of v at delta by this one. So now again we are replacing our del v del y by minus del u del x. So this is our equation number 4. Now we take this term, this one. Yeah. So second order derivative, its integration gives the first order derivative. So limit value, okay. Now what is the value of y at delta, or what is the value of del u del y at delta? Now we calculate it. Del u del y at delta. So from mathematics, limit. So we are taking 2 points. This is the value at this is at y equal to delta. At y equal to delta, the value of velocity is capital U. And what was the definition of boundary layer? From this point, if you go upward, the velocity is not changing. So at y is delta, the value is capital U, and at y is delta plus h, the value is also capital U, because beyond the boundary layer, the velocity is not changing. So from mathematics, the del u del y at y is delta will be 0. So if we substitute the limit values, del u del y at delta, del u del y at 0, upper limit, lower limit. The value of the upper limit gives 0, lower limit. Now nu can be written as minus mu by rho. When we derive the boundary layer Navier-Stokes equation, we have used the constitutive equation. This is our shear stress. Its formula is there. Okay. Now, what is the value of del v del x? If you use your order of magnitude approach, value of v is almost equivalent to delta and u is 1, y is delta. So what is the smallest order term? The first order of magnitude delta, delta square by delta means delta. The second one will be delta cube. So the second term is very much less than your first term. So that's why we neglect our second term. So what is this term? This is nothing but the shear stress. Mu into del u del y, this is nothing but the shear stress. What is the meaning at y equal to 0? Means what is the shear stress at y equal to 0? And we denote this term by tau naught. So what is our tau naught? This is mu del u del y at y equal to 0. This is the shear stress at y. So now we are using our equation number 4 and 5 in equation number 3. So we have used it. Okay. Now some simple calculation. Twice u del x. This can be written as del x of u square. Now one question might come. How could you write del x outside the integration sign? You see, your small u is a function of x or it may be y. Now you are integrating with respect to y. Okay, so you are integrating it. After integrating, you are substituting the value of y. So means this part is a function of x and your x and y, they are independent to each other. So you can write your del x outside the integration sign. Similarly, so in the same fashion, now you see for this part, what? Capital U del x of small. Again, you see capital U is a function of x only. So capital U can be written outside the integration sign. So for this part, we have used this one. So del x of product of two function. It is like this, del x of product of two function. It can be written as first function into differentiation of second plus second function into differentiation of. So from that, the value of this part, this one, will be del x of this y minus this. So we have substituted this value here and then some simple calculation, and using those two thicknesses delta 1 and delta 2, we have arrived up to this conclusion. So please you see. So these two terms are added and remaining two terms are added. From that two term ddx of capital U is taken common. ddx of capital U, you can put it inside the integration, you can taken out from the integration, it will not create any problem. So this particular equation is known as your momentum integral equation. In the same fashion, we have solved another one, that is the energy integral equation. So same boundary layer equation, I am not repeating it. So we have to solve the equation 1. So before that, what we do, we multiply both the side by small u and integrate with respect to y across the layer, that is from 0 to delta. So we have done it. Okay, integrating it. So now we take our second term. We will do some simplification on second and fourth term. So this is the second term. So same, we are using by parts, or your second term can be written in this form, del y of half of u square. Just I do in side work, u square by 2. So this will be half. Now twice u del y. So 2 half. So u into del u del y can be written in this form. Okay. Now we do one more simplification. We have introduced capital Y square also inside the differentiations. You see, it will not create any difference. Why not? Because your capital U is a function of x only. It is not a function of y. So if you differentiate your capital U with respect to y, you are getting 0. So you are getting the previous. Just for the sake of calculation, we have used. So by parts, first function into integration of second minus differentiation of first into this. So when the upper limit is substituted, at y is delta, the value of small u is capital U. So this term is neglected. When y is 0, v is 0. So ultimately you are getting no term. The value of del v del ys minus del u del x is substituted here. You see. So this is the simplified form. Similarly, this one, same, first function into integration of second. This is your second order derivative, so its integration gives the first order. Same, differentiation of first into integration of second. Please, you see. Okay, second order derivative, its integration is del u del y. So now, when y is delta, the value of del u del y is 0. Just I have shown in your last article with that limit. When y is 0, the value of u is 0. So this is cancelled, only this is the remaining term. So same, some simple calculations you see. Now we multiply both the side by 2. Okay. Then we have added all this integration. Okay. And finally, yeah. So you can verify it. The whole part, this part can be put, or that can be written as differentiation of some expression. You can verify it. This is small u, and this is from your, this is nothing but, this comes from your energy thickness delta 3. Please, you see. So this is called your energy integral equation. I have already given this note in your WhatsApp group, and this video is for the explanation. So again, you please check all these 3 articles, and if you still have any query, then you please ask. Thank you.